In the previous video, we talked about a question that's commonly asked about vectors. The question being, does a vector's tail have to be fixed at the origin? And the answer to this question was that from one perspective, absolutely not. And from another perspective, absolutely yes. Okay, now from the absolutely not perspective, the idea is that when you think about how vectors are just simple quantities in the same way that scalars are simple quantities, with the only difference that vectors have a little bit more complexity since they have a direction associated with them. But in the same way that we have these graphical representations of vectors, with the length of the arrow representing the magnitude and the direction of the arrow representing the direction, we could also think about graphically representing a scalar like temperature or weight, and we could say that the diameter of this dot here corresponds to the magnitude of the temperature. And same idea with the weight, but since scalars don't have any direction, neither do these circles here. It's just a magnitude. So with that, then, we have these graphical representations here of scalars and vectors, which should give you a sense of how a vector is just a quantity that you assign to something in the exact same way that a scalar is just a quantity that you assign to something. And so now I asked you the question, okay, well, does a scalar have to be fixed at the origin or have to be fixed somewhere? Well, then that question is kind of a silly question, because the answer to that, as we know, is, well, this is just a quantity. In general, no, this isn't fixed anywhere. It's just a quantity that you assign to something. I guess it could be fixed at wherever the temperature you're measuring is, but in general, no, it's just a quantity. Well, again, a vector is a quantity in the exact same way that a scalar is a quantity. In general, it's not fixed anywhere until you assign it to something. If there's a vehicle driving by, I might assign it to that vehicle in the same way that I might assign a weight to that vehicle. And so from that perspective, you can see how, no, in general, a vector is not fixed anywhere. In general, unless you assign it to be fixed somewhere or to be directly associated with something in the same way that you would do with a scalar. Now, regarding the other perspective, in which you would say that a vector's tail is always fixed at the origin, what we're talking about from that perspective is we're thinking about the vector space that the vector is contained within. Any vector you can think about is part of its own vector space. So in reality, we can look at a vector this way. Okay, and from this perspective, what we can see is that you can think about how any vector is within its own little world with its own coordinate system. And this world we call the vector space of that vector. So here, this vector space is the set of all potential force vectors in 3D. And same idea here. This is the vector space of all velocity vectors in 3D. Now, but like present here is just one of those potential force vectors. But within this vector space, you can construct any of the infinite possibilities for 3D force vectors. I mean, you could still do a 2D vector. I mean, if you make one of the components equal to 0, then you're contained within a plane. But in general, we're thinking about it's 3 components, with one or more of those components being 0 if you want. Okay, and so to specify, let's say, a force vector, all you're doing is you're providing 3 components. A component of the force in this direction, a component of the force in this direction, and a component of the force in this direction. And the result you get is a force vector. But what you can see is that it wouldn't make sense to say that you want to specify a force vector that's within this vector space, this force vector space, that's located here. That wouldn't make any sense. The tail is not fixed at the origin what does this even mean? What's the component of the force in this direction and in this direction and in this direction here? I mean, really the main question here is, what does this mean in this context? So no, within a vector space, it doesn't make sense to have a vector's tail not be fixed at the origin. Okay, but now you might ask, well, then what does it mean that from this main coordinate system here, these vectors don't have their tails fixed at the origin? Right? If we hide the vector spaces, what does this mean? These don't have their tails fixed at the origin? Well, this means the same thing that having a scalar not fixed at the quote-unquote origin would mean. In a certain system, you could have the temperature of something be, so let's say this is X, Y, and Z. The temperature of something could be a function of X, Y, and Z. So the location is going to dictate what the temperature is. Same with weight. Well, you could do the same thing with vectors. Vectors are just quantities, like scalars are. And in this scenario, what you have is what's called a vector-valued function. This vector here could be a function of X, Y, and Z. All that means is that, depending on the location relative to this coordinate system, that's going to dictate what the vector is. You have, in this case, you have a different scalar value depending on X, Y, and Z. Here, you can have a different vector value or a different vector. If you're at one XYZ position, you'll have this vector. If you're at another XYZ position, you'll have this vector. Another XYZ position, you'll have this vector, force vector. That's it. And you could think about how you could associate the X, Y, and Z with each component of the vector. So, the component in this direction of the vector, like the X, I guess this would be, or the Y direction, would be a function of the location in 3D space. Same with this component. Same with this component. That's it. In this case, you have a vector-valued function, and you could look at this as a scalar-valued function. Okay, but now, with that, though, what are we talking about when we say vector space? A vector space, what does that mean? What are we talking about here? Well, a vector space has to do with the technical, mathematical definition, meaning of vectors. We really learn about this technical definition, the meaning of vector spaces in linear algebra. Now, this playlist here isn't a linear algebra playlist. This playlist is more just to understand the fundamental vector operations for vectors that we use in 3D space, in engineering, physics, force vectors, velocity vectors, momentum vectors, acceleration vectors, understanding adding and subtracting vectors, the dot product, things like that. However, because even these vectors that we use in physics are still technically mathematical vectors, the same vectors that we use that we work with in linear algebra, and because this question commonly comes up about are vectors always fixed at the origin or not, in which the answer to this question, you really need to think about the idea of a vector space, like we've just seen, then I thought it would be useful just to go ahead and talk about vector spaces very briefly. But we're not going to go too deep into it. That's for linear algebra. Okay, but just to give you a quick, brief overview, what a vector space is it's a very abstract way of defining what can be represented as a vector. It's very abstract, but it's abstract on purpose for good reason. And what it comes down to is if you've got a set of elements that obey certain properties in the sense that they're associative, they're commutative. So the order that which you add them doesn't matter, or the grouping in which you add them doesn't matter. Or when you add that quantity to zero, you get the same quantity back. Or if you multiply like the sum of two of these elements by a scalar, it just follows the simple distributive property. or when you add one of these elements to another one of these elements, you get that same type of element back. You get another element within that vector space. If you have a system of elements like this that have these properties, which means that you could define it as a vector space, then you can use all of the operations that we learn in linear algebra to analyze that system. Even if on the surface that system doesn't look anything like what we would typically think about as a vector. For example, in differential equations, when it comes to linear differential equations, a set of linear differential equations, all of the terms in these equations obey these properties. And so with that, you're able to use these powerful techniques in linear algebra to solve these systems of linear differential equations. And so that's a brief overview of what a vector space is. But if you're still confused about that, don't worry about it. This playlist isn't about linear algebra or vector spaces. But I'm just trying to give you a general sense of the meaning of what we're talking about here, and that a vector is within any vector that we work with is kind of within its own vector space.